So in this video, we are going to discuss about 4-bit adder and subtract. So first, let us discuss about 4-bit adder. So what is 4-bit means? Let us consider I am going to add 8 with 4. Okay. So if I 4-bit means I have to represent 8 as 1000. Okay. 4 as 0100. This is a binary value. So if I add these two bits, I will get the answer as 1100, and the carry of this one is 0. Okay, these are my sum values, and this is my carry value. So always the carry bit is 1. Suppose if I want to add 4 with 8, so again the answer will be 12, right? So here also you will get the answer as 12. So if we see how to add, how to represent 4, 0, 1, 0, 0 and 1, 0, 0, 0. So if you add this one, I will get the answer as same, right? Carry value 0. There is one more possibility. If I add 8 with 8, right, I will get the answer as 16. So if you represent 16, 1, 0, 0, 0, 1, 0, 0, 0, will get the answer as 1, 0, 0, 0, 0, 0. Right, it is nothing but 16. So here you can see the carry bit is 1, right? For the rest of the value, the carry bit is 0. So for this one, you can see in order to add these two bits, I require one half adder, right? Half adder, right? So if I add these two, I will get one sum and carry. We here the carry value is 0. So in order to add these 3 bits, I require one full adder, right? So I require one full adder. So again I will get a sum and carry. Here the carry value is 0. So if I add these three bits, I require another one full adder, right? So this is a FA2. So if I add this one, I will get a sum and carry, right? So here also the carry is 0. So if I add these 3 values, I require another one full adder, right? So I require 3 full adder and 1 half adder, right? So I can draw the circuit like this. This is one half adder, and this is one full adder. This is another full adder. So 3 full adders and one half adder. So let me term this value as this one as A and this one as B. Okay. So A3, A2, A1 and A0. The value is 1000. Okay. So I'm going to add this one with B3, B2, B1 and B0. Right. So that value is 0100. This is B. Okay. So if I add this one, I will get the answer as this. Okay. So here I can write this one as carry and this one as S3, S2, S1 and S0. These values. Okay. Corresponding values. Okay. So for the half adder, what are the inputs? A0 and B0. A0 I'm going to add. A0 I'm going to add with B0 in order to get the sum and sum S0 and I can write this one as a carry. This 0 value as carry, right? So this is your C1 value. Okay, let me term this. The C1 represent the carry of the first half adder output. Okay, so this is my half adder. Okay, in the half adder, I am going to add the input bit is A0 and B0. Okay, and the output is S0, and I am going to have a carry bit, that is C1. Okay, the half adder is the addition of the 3 bits. Sorry, addition of 2 bits. Full adder is the addition of 3 bits. So I am going to add A1, B1 with C1. So if I add, this is my A1, B1 with C1, I will get S1 and C2. This is my C2 value. Yeah. So I will get S1 and the output of this one is C2. Right? This is your C2. So again, this full adder is to add A2 and B2. So that I will get the answer as S2. And the output of this one is C3. Right? So now this one is again I added with A3 and B3. So in order to obtain the S3 and this one output is carry. Okay. So if I want to change this one into a full adder, so what is full adder? Full adder is addition of 3 bits. So I'm going to add make this one as a full adder, and I'm going to make one more bit C naught, and always that value must be equal to 0. Okay. So I'm going to change this entire thing with the uh, this is an IC 7483. IC 7483. It represent a 4-bit adder. Okay, so 4-bit adder means inside this one you have a 4 full adder. Okay, this is my IC, and this circuit is also called as ripple carry adder. So why it is mean as a ripple carry adder means is we can see the carry is ripple means it's like a wave. Okay, so the carry is um, generating like a wave. So you can see the carry of this carry signal is produced only when we obtain the value of C1, C2, and C3. So this is a disadvantage of this one. Okay, generally this is called as a 4-bit adder. Okay, so let me take IC 7483 pin diagram. So I'm going to write it this one. This is nothing but your you have A3, A2, A1, and A0 value, and you have B3, B2, B1, and B0 value, right? And the input is C0, right? Another these are my inputs, right? So that value is 1. This is 8, and these are the pin numbers, right? This is 10, and 2 is 3, and B3 value is 16, and this is 7, and B2 is 4. Okay, so what is C0 value is 13. Okay, so if you add this one, you will get 5 outputs, right? So 5 output is so this is a S3, and this is S2, S1, and S0, and this is a carry value. Okay, so the pin number is this is 14, and this one is this is 9, pin value, pin number. Okay, and so you can see it is a 16 pin IC. Okay, so starting from 1, so 1, 2, 3, 4, what happened to 5? So 5 is VCC. So for the this type of IC you require a supply and ground. So 5 represent the VCC, and 12 represent ground. Okay, so it is of generally of 5-volt value. Next I'm going to perform 4-bit subtraction. Okay, so generally what I'm going to do is there are 8 minus 4. Let me take the 8 minus 4. How to represent 8? 8 is this is 8, and this is 4, right? So since it is minus 4, I'm going to take this one 2's complement of this value. Okay, I'm going to take 2's complement of this value. So if I take the 2's complement value, so you have to invert this one, and I have to add 1. So if I invert this one, I will get the answer as 1 0 1 1. Then if I add 1 with this one, I will get 1 0 0 1 1 0 0. So 1 1 0 0. So if I now I'm going to add this one. So if I add this one, I will get the answer as 1 0 1 0 0. So 8 minus 4 is answer is 4. So here you can see this is 4, right? So you have to cancel this uh, carry value. So if the carry value is 1, you have to cancel this value. Okay. So now what I'm going to do is, for the full for this type of circuit, what I'm going to do, this is nothing but your 4-bit adder, right? This is your 4-bit adder circuit. So which will perform both the addition and subtraction, right? So you will have, so I'm not going to change the uh, A0, A1, A2, A3 values and all, right? So I'm not changing these. So if you see, there is no change with this A3, A2, A1, and A0 in the previous problem, right? So in the B3, B2, and B0, I have included one XOR gate, right? So what is the purpose of this XOR gate is, so if all the values to the XOR gate, if it is 0, if it is 0 means what will happen? This is nothing but B naught XOR with 0. So B naught XOR with 0. What is the formula? A XOR B is nothing but A B bar plus A bar B. So if this is B naught and this is 0, I'll get B naught into 1 plus B naught bar into 0. So the answer is B naught. So instead of, so you will get the answer as B naught. So similarly, you will get B1, this is B2, and this is B3. So generally, if I give 0 to this value, the same value, whatever the input that I am giving, will reach the output. So this will perform an addition. So if this I am going to write it as, now this is C naught. Okay, if C naught value is 0, it will perform the normal addition, right? So what will happen? C naught value is 1. If C naught is 1, so if C naught is 1, so what will happen? So this will become B naught XOR with 1, right? So if I change this one into, instead of 0, if I give this one as 1, so you will get B naught XOR with 1. So what is B naught XOR with 1? B naught XOR with 1 is nothing but, so you substitute in this formula, B naught 0 plus B naught bar 1. So it is nothing but B naught bar. So we get the answer as B naught bar, B naught bar, B1 bar, B2 bar, and B3 bar, right? So if C naught value is 1. So this is performing a 1's complement. So after that, what I have to do, I have to add this with one C naught, right? So then only it will become a 2's complement value. So if it is 0, it is performing addition. If it is 1, it is performing a subtraction, right? So you will get the output as, whatever the output you will get, carry you will get S3, S2, S1, and S0, right? So this is a circuit for adder and for subtraction. Okay. There is one more problem with this one. This circuit will not end here. Okay. So if we consider another, what is another problem? 4 minus 8. So if it is 4 minus 8, so here comes the circuit will not work for this type of inputs. So if 4 means I am going to represent this one as 0, 1, 0, 0. 8 means I am going to represent it as like this. Since it is minus 8, I have to change it into 2's complement value. So if it is 2's complement means, so I have taken the 2's complement value, then I am going to add this one, right? So if I add, I will get the answer as 0, 1, 1, 0, 0. So it is not minus 4. It is nothing but, this is nothing but 12. So this is not the value I'm going to get. So what I'm going to do is, again I have to take the 2's complement of this answer. Okay. So if I take the 2's complement of this answer, first you have to take the 1's complement of this value. 1's complement is uh, inversion of this value. Then you have to add 1 with this one. So if I add 1, I will get 1, 0, 1, 1, 0, 0. So this 1 represent minus, 0, 1 represent 4. right? So we'll get the answer as -4. So there is a problem occurs whenever this carry bit goes to 0. Carry out bit goes to 0, and the mode of the circuit, that is the C naught value. Here the C naught value is equal to 1. So now I'm going to form a table for this one. Okay. For mode, and that mode represent here it is C naught, and the carry represent uh, carry rep here the carry so I'm going to form one table. So this is my output. Okay. So 0 0 0 1 1 0 and 1 1. Okay. So there is no problem with the 0 0 values and all, right? There is a problem occurs whenever the 1 and 0, the circuit will not work. So what is my y value now? Y is equal to C naught carry bar. Okay. So I can write the y value is equal to C naught into carry bar. So what I'm going to do is I'm going to add one more XOR gate here. Okay, so one more XOR gate. Why I'm going to add one more XOR gate is because so I'm going to add one more XOR gate for this one. Since I want to make this as inverse of this value, right? So in order to get the inverse of this value, what I'm going to do, I have to get this input as equal to 1. When this value becomes 1, whenever the a value is less than b value, right? So this will happen only for the option is this is 1, this has to be 1, right? So I have to include one uh, AND gate, right? So this is 1, and this must be equal to 0, right? Right. So I'm going to invert this value, and I'm going to give it to this AND gate. Okay. So uh, so 1t. So I have to make A3, A2, A1, and A0, and the C0 is always equal to 0. So this is a structure of 4-bit adder, not subtract. So this entire circuit is meant only when the a value is less than b value, and um, for subtraction alone. Okay, for the rest of the values it will work fine. This will work fine only if we employ this circuit alone. Okay. So if whenever the a value is less than b, and we are performing the subtractions, we must include this circuit. To do it means instead of employing this circuit, what you have to do, so you have to make if you will get the answer, right? You will get the answer like uh, whenever the 4 minus 8, you will get the answer as uh, you will get some answer, right? It is in terms of 0 1 1 0 0, right? 0 1 1 0 0. So this value you have to give it to b3, b2, and b1 and b0. Okay, and you have to make a3, a2, a1, a0 as 0, and c0 also 1. Okay, for subtraction. Okay, so I can generally connect it to this circuit itself. Okay, this is your C0, right? So you can connect the C0 to this. So generally you can see this A is less than B means you have to perform the subtraction. For subtraction alone, this circuit this circuit you have to employ. So if you are not having this kind of circuit, for the output of this one you have to connect, make A3, A2, A1 equal to 0. Then you have to give this values. Okay, so once if we give this value, it will perform the 2's complement value, and it will produce the output as um, 1 0 1 0 0. Okay, so I hope this video is useful for you. Thank you.